Welcome, J&M. Okay, I thought another topic you might have some difficulty with is the IEEE 756 2008 representation of floating point numbers. Representation. You get it. So, basically, I'm not going to do one on IEEE 756. I'm going to do one on 2008 because 756 is rather simple. Basically, there are three flavors of this. You have decimal 32, decimal 64, and decimal 128. It's 2 to the 5th, 2 to the 6th, 2 to the 7th. Now you have a sign bit, 0 if positive, 1 if negative. You have a combination bits. Combination bits. You hear me. I don't have to write it well. That's 5. You have 5 combination bits. Now you have your exponent continuation bits. And here you have 6, 8, and 12. Then you have your decimal continuation bits, which is, well, an easy way to determine this is just add them up. 6 plus 1 is 7, plus 5 is 12, 32 minus 12 is 20, 8 plus 1 is 9, plus 15, plus 5 is 14, 64 minus 14 is 50, 5 plus 1 is 6, plus 12 is 18, 128 minus 18 is 110. So, how many decimal digits can you represent? Well, these guys will be in densely packed. So remember, densely packed, 10 bits, 3 digits. So you have 2 densely packed decimals here, that's 6 digits. You always add 1. I'll explain why later. You have 5 densely packed, that's 15 digits, plus 1 is 16. You have 11 densely packed here, that's 33 digits, plus 1 is 34. Okay, so these are concurrent, this segment here. They're all concurrent, they're all next to each other. Now, how do we do this? Okay, I'm going to focus on decimal 32. Let me write down the bias. Now, don't ask me where these came from. Just take it for what it is now. Basically, your exponents will have these biases. XS101, XS398, XS6196. For now, let's focus on decimal 32. Let's go back to a number we converted in the last tutorial, which was 25. Okay, you have a few rules here. One is your base, given the number m times b to the n, or to the e. Let's make it clear. B should be 10. M normalized to a whole number. So that's there. Make sure it's yeah, whatever. M is normalized to a whole number or an integer. And E prime is equal to the actual exponent plus the bias. So in this case, 101. Just follow that. Okay. Basically, that's it. And the m should be decimal. Okay. So, let's take 25. Let's make it more interesting. Let's make it 2.5 times 10 to the negative 5. Alright. So 2.5, we got base 10 is done. This one, well, m is a decimal number. It's in base 10, so that's right. But we don't have the bias correct. We don't have the normalization correct. We need to make this a whole number, so we move 1 to the right. That means we subtract 1 from the exponent. So your mantissa is 25. Your exponent is negative 6. E prime is your exponent plus the bias, which is 101. That is 95. Now you express the exponent in binary. So that's 1, 94 over 2 is 47, 1, 23, 1, 11, 1, 0, 1, 1, 0, 1. Okay. Let me check that real quick. Okay. Now the number of exponent bits you need is just the continuation bits plus 2, and I'll explain that in a while. So you have 8 exponent bits for this, you have 10 for this, you have 14 for this. So here's our 8. Let me recheck this. This thing is 31 plus 64. Yep. Okay. Now what? You now take 7 digits of your mantissa. So we have 25. How do we make this 7? Just add 1, 2, 3, 4, 5, 6, 7. Okay. Next step is to take the most significant bit of the 7 digits. That, of course, in BCD is this. If it starts in 0, what you do with the combination bit, first of all, sign bit. Sign bit is the easiest. This is a positive number, so we put a 0. Next is the combination bits. Now, here's the rule. If you're leading your most significant digit in the decimal, the mantissa, starts in 0, when it's represented in BCD, you place these two right here, and you place these 3 right here. I'll explain what happens when it's a 1 later. Okay. Next, you take the 6 bits that remain of your exponent. That's the exponent continuation bits. So 0, 1, 1, 1, 1, 1. Lastly, you take this thing and you express that with 20 bits using densely packed decimal. So densely packed BCD rather. So that gives us 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1. You have 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. Sorry, that's a 0 as well. Here you have 0, 0, 0, 0, 1, 0. Check bit is 0 since everything's here is 0. And you have 0, 0, 1. Sorry, 1, 0, 1 because it's a 5. Can't read my own writing through this camera. Anyway, so that's it. Basically, that's how you do it. Now, what if your leading bit is not doesn't start with 0? Let's say you have something like 9, 8, 7, 6, 8, 9, 5 times 10 to the third. /30th, whatever. Okay, so you move this normalized to the whole number. Comes 27. Now, sign bit is 0. E prime is simply 27 plus 101, or 128. That's very easy to convert because that's 1 followed by 7 zeros. Okay. Now you get the most significant digit of your decimal, your mantissa, and aha, it starts with a 1. So what do you do? Like I explained in BCD, if you have a 1 in BCD, these two are definitely going to be 0, 0, so you're only concerned about whether this is 0 or 1, because that tells you if it's an 8 or a 9. So we can just dump two bits here, 1, 1, to signify that, okay, our number starts with a 9 or an 8. And then we place the first 2 bits of our exponent right next to it. And then we place the important bit of our most significant digit in BCD after that. Again, 1, 1, exponent bits, BC most significant digit, last bit. Next, as usual, we copy this. Remember, this on sequence, so that's 6 zeros. And then you express the remainder of this in densely packed. So that's this one has 1 major, so check bit is 1. Major is at 0, 1, 2, so that's 2. Copy the last bits. You have 0, 1, and 0. Unaffected nibbles are this one and this one. Copy the middle. That's 1, 1, and 1, 1. 1, 1, 1, 1. Here you have 2 major. So check bit is 1. This is 1, 1. Major. The minor is at 0. So there's 0, 0. Copy the last bits at 0, 1, 1. 0, 1, 1. Unaffected nibble is this one. Copy the middle bits. 1, 0. See how fast it is? Imagine if I refer to the table. Anyway, there you go. You're done. Shall we try one with decimal 64? Yeah, this one's kind of a bitch because it's really big, but that's what she said. It's going to... Let's try it. So we have 3.8 73 to 1154 times 10 to the negative 23. So now we have to move this 1, 2, 3, 4, 5, 6, 7, 8 places. Subtract this by 8. Let's make this negative just for fun. So you have 1 as a sign bit. Your combination bits are now, well, your leading number is, it's not 3. Alright? You have 16 digits here. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. In fact, you have 10, 11, 12, 13, 14, 15, 16. Your most significant digit is 0, which is, of course, 0, 0, 0, 0. It doesn't match the criteria. So you can just copy the first 2 bits of your exponent. Well, we haven't computed our adjusted exponent yet, so let's take our e prime, which is negative 31 plus 398, which is 763. So that's 1, 183, 191, 45, 22, 11. I have 10 bits for this, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you copy the first 2 bits, and then you copy the last 3 bits. Then you continue, so you have 0, 1, 1, 0, 1, 1, 1, 1. And then you express the remaining digits here in densely packed. Now here really you have just zeros. Let's get to 387. Let me put the paperweight here. Okay, you have to express 387. Well, you know for a fact that it just leads with zeros because, well, we have an 8 here. That's the problem. So check bit is 1 because we have a 1 leading, and that's at the position 0, 1. Copy the last bits. Unaffected nibbles are 0, 1, and 1, 1. So 0, 1, 1, 1. And that's what follows. 0, 1, 1, 1, 1, 0, 1, 0, 1, 1. That's 3D7. 3, 2, 1 is straightforward because they're all, none of the digits are 8 or 9. Sorry, forgot a 0 there. 154 is just 0, 0, 1, 1, 0, 1, check bit 0, 1, 0, 0. And you're done. That is negative bullshit. Really just practice this. I'm out of time on my memory, but just practice this and it should come to you. Just watch this video over and over and see you next time.